Hello guys, how you doing? This is the eighth session of Fluid Mechanics 1 for Chapter 2. Uh, Today we're gonna talk about really important things, so please accompany me through the whole video. So, today's subject is about buoyancy, flotation, and stability, which is from section 2.11 of Chapter 2 of Fluid Mechanics 1. My name is Amir Raza Talagat and my email address is amirrazatalagat@gmail.com. Please don't hesitate to ask all of your questions which you have on your mind about the fluid mechanics, about this video, about the previous videos, etc. I try my best to take action and answer you as soon as possible. So, when we have a stationary body submerged in a fluid, there is a force which is going to be exerted on that. It is labeled as buoyant force, which is a net upward vertical force resulted from the pressure increase with the depth because the pressure of the upside is much less than the downside. So how we are gonna calculate it? Let's take a look at this picture. As you see, let me just bring it much more here. Yeah, we have a buoyant force at this direction. There's F2, F3, F4, and F1, which are the forces exerted on the body from four sides. There's a weight force here, and they're having a distance from the left side. So how we are going to calculate them? And also please pay attention to the height of the upside and the downside from the free surface. Let me bring it to the first position. Yeah. From the second Newton's law, FB is equal to F2 minus F1 minus weight. Since the direction of F2 is upward, the plus sign, and the F1 and the weight are at the downside direction, If we have a specific weight in a constant amount, we can have it as this. F2 minus F1 is equal to gamma H2 minus H1 multiplied by A. This term, guys, F2 minus F1 is here, from here. The weight is going to be interpreted as this equation. Gamma multiplied by H2 minus H1 multiplied by A minus total V. This means that gamma, let me just bring it here. This term, gamma H2 minus H1 A minus V total is this area, these blue areas. So the total formulation is that buoyant force is equal to the weight of the fluid displayed by the body, and it's directly upward. So if we want to identify the buoyant force of a body, we should utilize the weight of that body displaced by a volume, which is due to the upward vertical direction, and it is known as Archimedes principle. So Archimedes principle is telling about the buoyant force, which is the weight of the fluid, the weight of the fluid displaced by its body. As same as previous instructional sessions, we are either having momentum equations here, either. If we take the momentum of every force from point A, we can identify the location of the buoyant force which is exerted on the body. So doing all the calculation here is our main purpose. This term is also termed as VT, total volume. The equation 2.23 is extracted from this equation, so don't worry about it. It's not a new thing. So as I have told you, the buoyant force is going to pass through the center of the displaced volume, which means that the center of the displaced volume is the center of buoyancy. If we let me just see it here. Guys, if we want to consider a float body, there are some terms to be paying attention to. If the specific weight of the fluid are varying too much based on the depth, when we are going to calculate the buoyant force, if we have varied the specific weight, the center is gonna be the gravity of the displaced volume, not the centroid of the displaced volume. So as a result, if we have a fluid that has a varying specific weight, at the end the location of buoyant force which is exerted on is the center of the gravity of the displaced volume for float body at the varying specific weight volume. So there is an example here about buoyant force on a submerged object, which is example 2.10. Follow me with the written text in order to get it solved for you. Welcome guys to this part, which is the problem solving of example 2.10, subjected as buoyant force on a submerged object from section 2.11 of chapter 2. The question is, the 4-pound lead fish sinker shown in figure E2.10a is attached to a fishing line as shown in figure E2.10b. The specific gravity of the sinker is Sg equal to 11.3. Find the difference between the tension in the line above and below the sinker. We have to take the body diagram and apply the second law of Newton for that. Ta minus Tb is equal to weight minus F of buoyancy. W is equal to gamma sinker multiplied by total V, which is going to be gamma Sg sinker multiplied by V total. We know that from equation 2.22, gamma V is equal to Fb. So we can demonstrate Fb as W divided by SG sinker. If we provide it here, we're going to have TA minus TB as W multiplied by 1 minus 1 over SG sinker. It is 11.3. The weight is 0.4 pounds. So the difference is going to be 0.365 pounds. Welcome back, guys. There is one point to tell you about the example that I solved for you. At the example, as you have noticed, we have replaced the buoyant force on the hydrostatic pressure force. So pay attention to this term. Do not use both of them. Just use either buoyant force or hydrostatic pressure force. So I'm going to talk about the stability. Guys, when we have a body which is floated, there are 2 points to be paying attention to, which is the center of buoyancy and the center of gravity. When we have the center of buoyancy at the top side of the center of gravity, if we upside it down, if the body be upside down in a wave thing, it could be restored at the first place. Why? Because the buoyancy force is going to couple it up to be restored. At the other side, if the center of gravity be at the upside of center of buoyancy, for example, center of gravity is here and the center of buoyancy is here. If the flotation upside downs the body, it is not going to be restored, since the weight force is much more greater than the buoyancy force, which are you are seeing here. It is going to be overturning couple. There are some specific situations to talk about the stability. If you have a thin body and also the center of gravity be over the center of buoyancy, it could be restored. It is not a big thing, as long as we have we have told that if the center of gravity be above the center of buoyancy, it is going to be overturning couple. But if we have a tall thin body floating in a fluid, if the center of gravity be above the center of buoyancy, as long as it upside downs, the overturning is going to happen. So if you have a tall thing and the center of gravity be above the center of buoyancy, if we upside it down, there is a overturning couple and it is not going to turn in the equilibrium situation. So we have reached the final term of this instructional session. I'm really happy that you have accompanied me to this moment of the video. Please subscribe the channel in order to get the notification of following instructional sessions. And you can always see the video and provide your questions in the comment or in the email. I try my best to take action and answer you as soon as possible. And the last thing is, take care of yourselves and have a nice day. I bid you all farewell.